Thanks, Jim. And thanks so much for the organizers for being so flexible with this online portion. Uh, I'd like to tell you about some joint work with Jake Levinson and Alex Wu, connecting the combinatorics of the delta conjecture and the geometry of Springer fibers. So here's a really big outline. So the talk is primarily about geometric representations, so connections between geometry, representation theory of the symmetric group, and combinatorics. And the classic case for us will be the flag variety, the complete flag variety. And its cohomology ring is the ring of co-invariants from invariant theory. And the associated combinatorics is the combinatorics of the symmetric group permutations. Still classic, but a little bit less common are the Springer fibers, whose cohomology rings are sometimes called the Garcia-Perchesi modules or de Concini-Perchesi modules. And its associated combinatorics is in terms of tabloids. But more recently, Hagelin, Rhodes, and Shimazono introduced these RNK rings in connection with the delta conjecture and studied its connections with ordered set partitions. And even more recently, Pawlowski and Rhodes found these varieties XNK of spanning line configurations that give a geometric model. And last year at FPSAC, I talked about a new family of rings R and lambda that generalize all three families and its associated combinatorics in terms of ordered set partitions. And at the end of my talk, I asked for a geometric model for these rings. And so that'll be the topic of this talk, is a variety that we like to call the delta Springer variety, whose cohomology ring is this ring R and lambda, and which also gives a new geometric model for these RNK rings. So first, some background on Springer fibers. And to get there, we need to talk about the complete flag variety. So the complete flag variety is the space of all complete flags, which are nested sequences of subspaces of C to the n, where you start with a line and then you continue with a two-dimensional subspace that contains that line, and so on until you get to the entire vector space. And the complete flag variety is partitioned into cells called Schubert cells. So given a permutation, a Schubert cell is the set of all complete flags that meet the identity coordinate flag in certain dimensions, depending on the combinatorics of the permutation W. And why do we like these Schubert cells? Well, because if you take the closure of the Schubert cells, you'll get the Schubert varieties. And if you take the Poincare duals of the homology classes of those, you'll get a free Z basis of the cohomology ring of the complete flag variety. And there's lots of nice combinatorics, associated combinatorics in terms of Schubert polynomials. And in particular, the cohomology ring is free of rank n factorial. And another way to think about the cohomology of the complete flag variety is in terms of Borel's presentation as the co-invariant ring, where you mod out the ring of polynomials and variables by the positive degree homogeneous symmetric polynomials. And in order to define a Springer fiber, fix a nilpotent operator, nilpotent matrix, with some Jordan type lambda. So this means that the sizes of the Jordan blocks are recorded by the parts of this partition lambda. And then the Springer fiber is the set of all complete flags that satisfy certain linear conditions. Essentially, this is saying all of the complete flags that are invariant under acting by this nilpotent operator. And here are a couple of examples. So if your partition has parts all size 1, then your nilpotent matrix has blocks of size 1 by 1. So the only nilpotent matrix that's possible is the 0 matrix. And if you plug that in up here, you get a trivial condition. So you get all complete flags. So the complete flag variety is a special case of a Springer fiber. And then at the other end of the spectrum, if you take your partition to have only a single part of size n, then your nilpotent matrix is going to be a single Jordan block. And if after thinking about it a little bit, you can realize that the only complete flag that satisfies these conditions is the identity flag. So here EJ is the span of the first J coordinate vectors. So the Springer fiber in that case is just a single point. And then as you vary your partition, you get different subvarieties of the complete flag variety of varying dimensions. And the Springer fiber has lots of nice combinatorics coming from the geometry of its cell decomposition. And to get a cell decomposition, we'll need a weaker version of a notion of a cell decomposition called an affine paving. I'm not going to define it here, but it's just a partitioning of the space into copies of affine space in a certain way. And the Springer fiber has an affine paving. And if you choose your basis correctly, you can work it out so that the cells are intersections with Schubert cells. And there's a nice bijection that allows you to give combinatorial conditions for when one of these intersections, when one of these cells is non-empty. So it turns out that the non-empty cells are in bijection with row decreasing fillings of your partition shape of the Young diagram of lambda. So here's an example down below of what the Springer fiber for 3,1 looks like. It is a complex curve. So what I've drawn in down below is real 2 dimensions. And it's a bunch of Riemann spheres connected in a line. And so the first row decreasing filling is a single point. And then the next row decreasing filling here is a punctured sphere. And the next row decreasing filling here represents this punctured sphere. And then finally, the last row decreasing filling represents this punctured sphere. There are different conventions for how to do these fillings. You could reverse the labeling to get a row increasing filling, but I'm just going to do row decreasing filling because it'll be convenient for the geometry. And then the irreducible components also have combinatorial meaning. So if you look, the maximal dimensional cells down here are indexed by all of the labelings that are also column strict, so column decreasing. And if you reverse the labeling, you'll get a standard Young tableau. So the irreducible components of the Springer fiber are in bijection with standard Young tableau. And there's also a nice formula for the dimensions of each component. It's the statistic n of lambda that appears in McDonald theory all the time. And it turns out that those geometric properties are in some sense a shadow of representation theory statements. So if S upper lambda is the spect module, the irreducible symmetric group module indexed by the partition lambda, when Springer studied these varieties, he noticed that although there isn't a symmetric group action on the variety itself, there is a symmetric group action on the cohomology ring of the Springer fiber. And if you look at the top non-zero degree cohomology group, this is 2 times n of lambda cohomology group. The symmetric group modulo that you get is an irreducible module, the spect module S lambda. And so there's a bijection between Springer fibers up to isomorphism and irreducible SN modules. So this is in type A, and other types you have to change that statement a little bit. So I would say that the Springer fibers, in the sense, geometrically construct all of the spect modules. And if you don't just care about the top cohomology group, and you also want to know the graded symmetric group module type, there's also a nice formula for that. So here, this is the graded Frobenius characteristic, which sends graded SN modules to symmetric functions with coefficients in Q. And this is the modified Hall-Littlewood symmetric function. So this is due to Hatta and Springer, and I also I also put Garcia and Perchese here because they reproved the statement in a more elementary manner and worked out a lot of the combinatorics involved in the statement. So now I'd like to talk about the delta conjecture, the other side of the story, which is more recent. Here's just a very brief summary of some of the things going on in terms of the delta conjecture. So Mark Heyman proved that the graded Frobenius characteristic of the diagonal co-invariant ring has this very nice compact formula. So here xn and yn are 2 sets of variables, and Sn is acting diagonally so that they permute the x's and the y's simultaneously. Where here, delta prime is a certain operator on symmetric functions defined by Bergeron, Garcia, Heyman, and Tesler. The shuffle theorem, which was proved by Carlson and Mellett, gives a nice combinatorial formula for this symmetric function. And people started wondering, well, Hagelin, Rimmel, and Wilson started wondering, is there some kind of variation of this story where you replace this symmetric function with something else? And they just replaced this n here with a k and conjectured two really beautiful combinatorial formulas for the resulting symmetric functions. And not so long ago, the rise formula for that conjecture was proved by 2 different groups, Dederian, Mellett, and Blasiak, Heyman, Morse-Pun, and Seelinger. Although to my knowledge, I think the Valley version is still a conjecture. And they generalized the conjecture in 2 different ways. You might ask, well, is there an algebraic or a geometric model for these symmetric functions? And Zebracki has a conjecture, but I'd like to focus on the t=0 case of the delta conjecture. And in that case, Hagelin, Rhodes, and Shimozono found an algebraic realization. So they wrote down this ring of generalized coinvariants where you mod out by certain elementary symmetric polynomials and variable powers. And they were able to prove that the graded Frobenius characteristic of that ring is equal to the expression from the delta conjecture after you apply some minor involutions to it. So I would say that this gives an algebraic model for the delta conjecture at t=0. And Pawlowski and Rhodes found a geometric version. So they defined this space of spanning line arrangements and tuples of lines that span C to the K, and proved that the cohomology ring is RNK, giving a geometric meaning to the delta conjecture at T equals 0. And they also connected it with a lot of the combinatorics coming from the delta conjecture. So for example, they found an affine paving where the cells are indexed by ordered set partitions. Okay, so in this last part, I'd like to introduce to you a new family of varieties that we like to call the Delta Springer varieties that generalize a lot of the previous story. So in order to define it, we'll need a generalization of Springer fibers to partial flag varieties. So if you fix a composition alpha, FL alpha here is the partial flag variety of partial flags where the jumps in dimensions are recorded by the parts of alpha. And the Spaltenstein variety is a version of a Springer fiber, but for partial flags. So you take all partial flags of this type, such that when you act by your nilpotent, you get a subspace of the previous subspace. And these also have nice combinatorial properties. Fress and Brunden and Ostrich found affine pavings for these Spaltenstein varieties. There's another version of a Springer fiber for a partial flag variety called a Steinberg variety. Those are different, but those also have nice properties. So here's the Delta Springer variety. So given two integers k less than or equal to n, this time we'll allow our partition to be a partition of the smaller integer. So size the smaller integer. And I'm also going to throw in this extra parameter s. It's not as important. It's essentially the number of allowed rows in our labelings. So you take little lambda, and what you do is you append on this large rectangle, s many rows, and enough columns here. It doesn't matter as long as you have at least n minus k columns. So might as well let it be an s by n minus k rectangle. And so that's the partition capital lambda. And let pi n be projection from this certain partial flag variety down to the first n parts of the flag. And you can simply define the Delta Springer variety as a projection of a Spaltenstein variety. So this is the Spaltenstein variety where the nilpotent is type capital lambda. And the partial flags start out as looking complete, but then they start having these jumps by dimension s minus 1. And you take that Spaltenstein variety and you project it, and you just look at the first n parts, the part that sort of looks like it's complete. There's also a second definition. So if you want to think about these in terms of the projected flags, there's also a description that looks a little bit more like a Springer fiber. So it's a partial flag of this type that looks complete at the beginning, but then stops. And then you throw in your usual Springer condition, that linear condition, but then you also have to throw in a containment condition here so that the last subspace doesn't go off in too many directions. So it's essentially like a Springer condition combined with this Schubert condition, Schubert containment condition. And these Delta Springer varieties have nice combinatorics in terms of their pavings as well. So they have an affine paving where if you choose your basis correctly, you can work it out so that the cells are intersections with Schubert cells. And there's a combinatorial condition for when your cell is non-empty in terms of labeled diagrams. So they're in bijection with row decreasing partial fillings of capital lambda with the letters 1 through n, so that all of the labels are right justified, and so that the little partition is always filled. So you can, so these always have to have labels in it, and then you can have some other boxes with labels in it. Since we're only using the letters 1 through n, and the size of capital lambda is much larger in general. And there's a condition for when you get a maximal dimensional cell. And that's when the labeling in the little partition is row and column strict. So decreasing along rows and columns. And all of the extra labels are in the last row. And it turns out that the closures of the maximal dimensional cells give you all of the irreducible components. So the irreducible components can be described combinatorially this way as well. Another way to say this is combinatorially is just take this diagram and chop off the little lambda part, and you'll get an injective filling of little lambda that is row and column strict. So the irreducible components are in bijection with the row and column decreasing injective tableau. And there's also a nice formula for the dimensions of each irreducible component. So these things are pure dimensional as well. So here's the connection with the delta conjecture, is that when your partition is 1 to the k, and your number of allowed rows is equal to k, then there's an easy bijection between these cells and ordered set partitions, where you just take the first row and you interpret that as the first part of your ordered set partition, and you take the second row and make that your second part, and your third row and make that the third part of your ordered set partition. And we were able to prove that these varieties also give a geometric model for the delta conjecture at t equals 0. So instead of the spanning line arrangements, which are have different geometry, the spanning line arrangements are smooth but non-compact manifolds. These are compact but singular varieties. And we've also generalized the Springer correspondence to certain induced spect module representations, induced spect modules. It turns out that the cohomology ring has a nice presentation as a quotient ring, and they match up with the rings that I talked about in my FPSAC talk last year that appear in my thesis. That was one of the main motivations for looking for defining this variety. So you can use the presentation to find an SN action where SN just permutes the variables. And if you look at the top non-zero cohomology group, you get an induced spect module. So essentially the induction product of S lambda with the trivial representation, or what you get by tensoring S lambda with the trivial and then inducing up to Sn. So I would say that the delta Springer varieties geometrically construct all of these induction products. So these are the ones that are given by Pierre rule. Or in terms of symmetric functions, it's a Schur function times a complete homogeneous symmetric function. And lastly, there's also a nice graded Frobenius characteristic formula. So a realization of its graded SN module type. So Rhodes, Yu, and Zhao defined an inversion statistic for these label diagrams. You'll probably see Tianyi draw these in a different manner. So rotate the diagram. I think Tianyi might also flip the diagram later in their talk. So they defined an inversion by looking for attacking pairs. So an attacking pair is two labels B greater than A, where B and A are in one of these configurations. So they defined an inversion statistic using these attacking pairs, and they used it to find a Hilbert series for these rings Rn lambda S and a space of harmonics, which we'll hear about later. So stick around to see that talk. And it also turns out that you can get a graded Frobenius characteristic formula just by allowing the labels to repeat in a single column, and then keeping track of the inversions and the labels that you use in a monomial. And there's also a variation in terms of diagonal inversions that gives you an LLT expansion. And last, I'll mention some other properties of these delta Springer varieties, which is that if you take the limit inductive, if you take the direct limit of these spaces as S goes off to infinity, that's the cohomology ring of that infinite dimensional space of that ind variety is isomorphic to the coordinate ring of a certain scheme, which generalizes work of De Concini and Perchesi. And also forthcoming work, which is that the inversion statistic and diagonal inversion statistic actually have geometric meaning, which is that they compute dimensions of the cells. And if you count points over FQ, you can get a Hall-Littlewood expansion of these graded Frobenius characteristics. And then I'll leave you with some further directions. My main question being that, is there some kind of QT parameter version of these symmetric functions where if you set t equals 0, you get back to the graded Frobenius characteristic? So thanks for listening.
Thank our speaker. So I had just one comment myself on that last question. Is there a QT? I was looking at if you go back a few slides to the diagram with the back one more there. So this B over A thing, and this is basically what you would get if you let t equal 1 in the Macdonald polynomial.
Right.
You didn't have a basement. So I wonder if you could just put the t's in that way, what would happen? I don't know.
I'm not even sure if that's symmetric. Well, I'm not even sure if that's sure positive. I'd have to check that.
Okay. I see.
But that's a good idea, is that maybe, and so I'm having these like 0 descents. So maybe just allow any labelings and then keep track of major index statistic and what is that symmetric function.
Mm-hmm.
Yeah, that's a good idea, but I haven't looked at it yet.
Okay, so I guess we're out of time. Thanks. Let's thank our speaker again.